So I'm Iryna Kushniruk. I'm a postdoc working at Stockholm University, Sweden, and today I'm going to talk about the GALAH survey, what it can tell us about the stellar halo. So let's move on to the next slide. And we know that the stellar halo is one of the major structural components of the Milky Way. And we know that it assembled through a large number of accretion events. And in order to trace these accretion events, we need to know kinematics, elemental abundances, ages for as many stars as possible. So methods of galactic archaeology can help us to better understand the Milky Way's formation, and in particular, the formation of the stellar halo. Also, in this talk, I will refer a lot to orbital actions, such as JR and LZ. And orbital actions are quantities that are conserved in time, assuming axisymmetric potentials. And radial action is this quantity, and it's a measure of orbit eccentricity. And LZ is azimuthal action, and it's the same, it's equal to the vertical component of the angular momentum. Okay, so we keep that in mind and move on to the next slide that shows a number of already known accretion events in the halo. It's for the illustration, and I borrowed these plots from Koppelman et al. Paper. So it shows 1, 2, 3, 4, 5 accretion events in the velocity space, as well as in the elemental abundances space. And we can see that these groups, they actually stand out and they are different from the disk stars. So it's perfect to trace them in kinematics and elemental abundances spaces. Except that we know that mergers can hit the disk. And for example, these plots I borrowed from Belakurov et al. Paper, and they show V-phi versus metallicity. If we compare the populations, we can recognize thin disk, thick disk, sausage, Sequoia, and the heated thick disk, which is called the splash. And here I provide a citation from the paper, stating that the splash stars may have been born in the Milky Way's protodisk prior to the massive ancient accretion event, which drastically altered their orbits. So mergers can hit the disk. Except that it's interesting to discuss the inner galaxy substructure. Why is it so interesting? Because, for example, if we select, if not we, but Hort et al., all these plots are from their paper, select stars based on magnesium, manganese, aluminum, iron, and, for example, plot just accreted stars, we can recognize Gaia Enceladus sausage and one more structure that has the same angular momentum. Also, they are separated with the gap, and that's, I think, particularly interesting. And this structure is called the inner galaxy substructure, simply because it's localized in the inner part of the galaxy. I also provide a citation from the paper stating that Gaia Enceladus sausage from this analysis seems to be more chemically evolved compared to the inner galaxy substructure, and that's a bit unusual. So, for example, if we assume that both groups originate from the same progenitor, the progenitor should have a positive metallicity gradient, which is uncommon. Okay, so we have this number of accretion events, heated disk, etc. So we would like to learn more about it. We would like to learn more about the mass of the Gaia Enceladus sausage and the inner galaxy substructure, which is relevantly new. And we have the GALAH survey that can help us to answer these questions. So we selected roughly 40,000 stars from the GALAH DR3 survey. Selection criteria is listed here, and these are mainly giant stars. And in order to get the stellar overdensities, we applied the wavelet transform method. It's a main formula where F is the input to the input map, and it's a bint 2D distribution. For example, in our case, it's a GR LZ distribution. And psi is the wavelet function. For example, compared to the Fourier transform, we have sine cosine functions that are infinite, but wavelets, they drop to zero quickly. So that's the main difference. So what happens if we apply wavelet transform to 10,000 Monte Carlo maps and overplot them together? That's what we get. And I think this is the key result of my talk, showing LZ versus JR distribution, what we get with the wavelets. And now it's time to recognize, to identify the structures. So what we see is the disk. That's more or less clear, it's huge. And how about the rest of the structures? I provide a comparison plot from Fouillet et al. Paper, and it shows that stars above 30 in JR are usually associated with Gaia sausage Enceladus, and we also get peak above 30, and that's the pure Gaia Enceladus sausage population. If we move on to the splash, we can recognize two substructures. That I think is new, and yeah, we need to understand why exactly, what could lead to this double double peak nature in the splash. For comparison, I have V5 versus metallistic plot from Bellacuro, and what happens if we select stars inside these ellipses and make the same distribution. So we can see that it's orange and gray and black dots. They actually follow the same pattern. And to convince you that we observe this double peak nature in the splash, I show you the same plot, but just jet color scale. It's the same plot, but just another color scale. Let's move on to the inner galaxy substructure. We also see it in our GALAH sample. And for comparison, I have energy versus LZ plots from Horta et al. And yeah, we can see that the inner galaxy substructure is indeed there. And to convince you that it's actually the inner galaxy substructure, I show you the plot R, which is distance to the galactic center, versus module Z, and its distance from the galactic midplane. And we can clearly see that the cyan dots, they are indeed localized close to the galactic center compared to Gaia Enceladus sausage stars that are mainly in the outer parts of the galaxy. So the question is still there, why Gaia Enceladus sausage is more localized in the outer parts, why the inner galaxy substructure is in the inner part, why it's not one thing. And to answer the questions like that, and also how different chemically are these two populations in the splash, we show box plots for different elements from the GALAH survey for different populations. So this is Gaia Enceladus sausage, inner galaxy substructure, splash 1, splash 2, thick disk, thin disk. But that's what happens. It's just one part of the plot. We have more elements. And let's look at the alpha elements. For example, magnesium. We confirm the same results, and calcium looks the same as Horta et al., that the inner galaxy substructure is less chemically evolved than Gaia Enceladus sausage. Let's look at, for example, titanium, the same thing, oxygen. Also for selecting stars in the Gaia Enceladus sausage, we can see that sodium works well, magnesium works well. Again, going back to our process elements, we have a europium here, and we can see that it's slightly higher up compared to the rest of the groups. So that's where we are, and let's look also at the splash 1 and splash 2. There is some difference, but it's not drastic, I would say. It looks like something in between the halo and the disk populations, where this green substructure looks more like the thick disk. So I think it's now time to show you the summary plot, not plot, the slide. And I also would like to thank our team members who also helped me to get the results, and it's Karen Lind and Chris Joachim. Also, Chris's talk is scheduled for today as well in roughly 20 minutes, so follow his talk. And the summary. So we selected a sample of roughly 40,000 giants from the GALAH DR3 survey, and we detected Gaia Enceladus sausage, the inner galaxy substructure, splash, 2 subgroups, Thamnos that I actually did not mention, but yeah, we do see Thamnos as well in our plots, and the disk. What we see is that Gaia Enceladus sausage is more chemically evolved compared to the inner galaxy substructure, and we confirm results of Horta et al., who proposed that both groups do not originate from the same progenitor and are actually 2 separate accretion events. We also see that Gaia Enceladus sausage extends a bit lower in square root GR, not 30, but maybe 20, but in this lower part, it's more contaminated by the splash population. So is Gaia Enceladus more massive than we thought before? Is it bigger event than we thought before? And also the question is why Gaia Enceladus sausage and the inner galaxy substructure have the same LZ? But inner galaxy substructure is localized in the inner part, and Gaia Enceladus sausage is located mainly in the outer parts. And the dual nature of the splash. So what could cause this dual nature? Can it be somehow connected to 2 different merger events? So I'll leave you with a number of questions that we still need to answer. And thank you.
Thanks, Iryna. That's well on time. You have 3 minutes left, I guess. That gives us more time for questions. Who wants to start? Let's see. Again, either raise your hand, post a question in the chat, or just speak up. In the meantime, if people still sort out their questions, I have one. With regard to the low or the extension to lower JR, you discussed that Gaia Enceladus might be more massive, but can't it be that also the orbit of the exact merging orbit might play a role in that? And so my question, I guess, goes into the direction with those measurements. Is there any way to basically get constraints on possible orbits for the progenitor? Do you have an idea for that?
So we actually checked eccentricity of stars in the Gaia Enceladus sausage population, and it's the same result as most of the other papers showing that it's super eccentric and has eccentricity about 0.9. Also, if we check these stars, yeah, it's more contaminated by a bit lower eccentricity group stars. So yeah, as I mentioned, that this part, we do see some stars that have Gaia Enceladus sausage like kinematics and chemical partons, but it's more contaminated by the splash. So we still think that there is some fraction of Gaia Enceladus sausage in this lower part, especially if we look at this different color scale. You can clearly see double splash, and that it's somehow connected to this upper part, which we think is Gaia Enceladus sausage plus splash.
Okay, yeah. And then thanks. We have a question by Sarah Mattel.
Yeah, hi, thank you. Iryna, thanks. This has been really interesting to listen to. I'm thinking the GALAH sample is all fairly nearby in the galaxy, and yet you're seeing multiple substructures. I'm wondering if you had a volume over a larger, if you had data over a larger volume, do you think you'd see different substructures, or do we have a good expectation for that yet?
So right now we explored just the GALAH DR3 sample, and we explored giants. So it gives us some flexibility.
Okay, so that's a decent size.
Yeah, yeah.
Okay, good. Good.
And also, if we look at the R versus that, we can see that still have some stars everywhere, not just, yeah, I know that GALAH survey covers, as far as I remember, 80% of the stars are located in the solar neighborhood. Yeah, but
Yeah,
with the,
well, that's what I was thinking. Yeah.
yeah.
Okay, thank you.
Thank you too.